most important responsibilities of an air traffic controller are ensuring planes are safely separated from each other while maintaining the most efficient flow of air traffic. Accomplishing this is complex and labor-intensive. Air traffic controllers must keep aircraft properly separated as they move throughout the system. In a busy airspace like Southern California, a single controller is responsible for simultaneously directing aircraft for multiple airports. Wind direction and velocity determine departure and landing direction. Aircraft generally must take off and land into the wind. Southern California airports typically experience westerly winds, which require planes to take off and land to the west. When in a west flow, air traffic control sequences arrivals from all directions. These arrivals are sequenced to land on 2 runways simultaneously. Aircraft are sequenced and merged into each arrival stream. LAX serves many destinations. When aircraft depart to the west, an initial heading is used, then planes fan out to specific departure routes. The departures and arrivals have numerous crossing routes where the departures must be separated from arrivals. Controllers continuously manage and separate arrivals and departures simultaneously throughout the day. Adding to this complexity in Southern California are the numerous aircraft operating at multiple surrounding airports in this crowded airspace. Aircraft flying at the same altitude must remain a minimum lateral distance from each other. In airspace surrounding airports, the minimum lateral distance is 3 miles. In higher altitude airspace, the minimum lateral distance is 5 miles. If aircraft don't meet the lateral separation requirements, they must remain a minimum vertical distance from each other. Below 41,000 feet, the minimum vertical distance is 1,000 feet. Conventional procedures utilize ground-based navigational aids, or nav aids. This picture shows a nav aid. We first started using nav aids in the 1940s, and the basic operational concept has remained unchanged since then. These decades-old radio beacons are used to direct aircraft along routes that require them to fly from point to point. All over the country, we are replacing old routes that use nav aids with new routes that rely on global positioning satellites, or GPS. The accuracy of GPS allows us to develop more precise routes that provide separation from one another. The revolutions in navigation sharing of data have changed the way you conduct daily life. Just as the internet has altered how we communicate, new technologies have transformed the way we fly. Airplanes at airports that make up our transportation system don't look much different than they have in the past decade or two. However, the ways in which they are guided and controlled are changing significantly. Satellite navigation and new ways in sharing data are creating benefits by enhancing safety and efficiency of aircraft operating throughout the national airspace system. Satellite-based routes aren't just making today's system safer and more efficient, they're also laying the foundation for further improvements to safety and efficiency. One example is time-based metering. This system allows us to precisely meter the flow of aircraft to and from airports by knowing with greater predictability where an aircraft will be at a specific time. Time-based metering is key to the evolution of our air traffic control system. We call this evolution the Next Generation Air Transportation System, or NextGen. Satellite-based procedures are a significant element of time-based metering. Once NextGen is fully implemented, we'll be able to tell where each aircraft will be at any point in time along the way to its destination. This will be a tremendous enhancement to our ability to manage traffic more safely and efficiently. A traditional descent is like walking down a flight of stairs. Based on air traffic controller instructions, the pilot descends and applies speed brakes, then levels off and powers the engines up, then descends and applies speed brakes again. The cycle repeats itself until the plane is on its final approach to an airport. By contrast, an optimized profile descent, or OPD, has built-in speed and altitude requirements at various points on the route. This information is programmed into an airplane's flight computer and allows them to essentially glide down to an airport on idle power, and controllers don't have to issue instructions after clearing the plane to begin its descent. An OPD and optimized climb profile are much more efficient than traditional descents and climbs, and there are key benefits that we're seeing today from our use of satellite-based routes. An OPD and optimized climb profile are much more efficient than traditional descents and climbs, and they're key benefits that we're seeing today from our use of satellite-based routes. OPDs are safer in that there is less pilot-controller interaction. Airplanes flying OPDs versus a traditional descent generate less noise and emit less pollution because their engines are near idle and speed brake use is minimized. An optimized climb profile is the reverse of an OPD. It allows a plane to climb unrestricted to its cruising altitude, separated from other crossing traffic. This video provides a basic understanding of how the air traffic control system works, how the FAA is modernizing through NextGen, and why it's necessary. The Southern California Metroplex presents unique challenges, with many pilots telling you we have the most complex airspace in the country, if not the world. Southern California has a large number of airports, routes that weave under, over, and around each other, high traffic volume, mountainous terrain, with blocks of military and special use airspace that's often unavailable for civilian use. All of these factors were taken into consideration with the new Metroplex routes.